Andreas Trautner and Adam Smetana. So yeah, let me start. So I think your first and reasonable question would be, why not standard model neutrino self-interactions with just normal Z boson? So the answer is pretty simple, that first, as any weak process, it is very much suppressed by the mass of the mediator. And the second, the more important, that the detection of such a process, neutrino on neutrino scattering, would be too complicated. And so the direct observation of neutrino scattering via Z boson is yet beyond current experimental capabilities. And from the other hand, beyond standard model theories, they give us very appealing solutions that include beyond standard model neutrino self-interactions, which don't have fixed mediator masses or couplings, and this allows us to consider bigger interaction rates. So I'll start with the neutrino self-interaction motivation. So as I mentioned before, it comes from beyond standard model theories, which often offers you dark matter neutrino interaction models, some spontaneous breaking of lepton number symmetry Myron models, and also they introduce neutrino self-interaction for neutrino mass generation. And also neutrino self-interactions, they are a great portal to new physics because they can connect you with the dark matter. And also they are cosmologically relevant. They appeared to a kind of solution to possible solution for resolution of cosmological tensions such as Hubble tension and matter power spectrum. And they are not yet excluded by data. So because neutrinos are still very mysterious particles, there are plenty of models which are named under the neutrino self-interactions. First of all, it can be Dirac neutrinos or Majorana neutrinos that we consider. Second, we can have coupling between active and active neutrinos, active and sterile neutrinos, active and dark matter. There are respective Lagrangians which are written on the slide. Also, there can be different coupling to neutrinos. There can be flavor universal coupling or flavor non-universal coupling. And there are different types of mediators which can mediate these interactions. For example, massive scalars, pseudoscalars, vectors, or axial vector fields. In this work, in this seminar, I will consider a scenario where neutrinos are coupled to massive scale or to vector scalar. What else? It's also Dirac neutrinos, and mass and coupling strengths are free parameters, and we are going to investigate them. So now we will address to the literature, and we will see how neutrino self-interactions can be measured and constrained, and was constrained via previous research. So there are many ways to constrain neutrino self-interactions. It can be through cosmology, astrophysics, solar physics, and laboratory. So we will start from cosmology. So neutrino self-interactions modifies how neutrinos behave before and after they decouple. And if neutrino self-interactions are present, neutrinos can remain coupled for longer, and this has lots of consequences. And respectively, in the absence of neutrino self-interactions, neutrinos would decouple early and free stream. So Starting from Big Bang nucleosynthesis, the presence of neutrino self-interactions would alter the expansion rate and can shift the neutrino to proton ratio, and this affects the predicted abundances of light elements like helium and deuterium. Also, it can affect neutrino microwave background because neutrino self-interactions again would suppress free streaming of neutrinos at the early times, and delay the epoch at which neutrinos begin to free stream. And compared to the standard lambda CDM model, neutrino self-interactions shift a cosmic background power spectra peaks towards smaller scales. And there we have also a large-scale structure and matter distribution in the universe. So if there are no free-streaming neutrinos, then matter clustering on small scales is altered, and this is altering the matter power spectrum. And it also alters universe expansion and, as I mentioned before, Hubble expansion rate. So there are also laboratory bounds which come from invisible Z boson decays and invisible Higgs decays. The examples of such a process you can see on the slide. There are also rare meson decays, tau decays, neutrino-less double beta decays, pion decays, and collider searches. So on this slide, you see that first in the small mediator mass region, you have cosmological constraints from BBN, from CMB. Then you have experimental constraints from double beta decay, from rare meson decays, from invisible Z boson decays. And there's also should be Higgs boson decays, but it is like more in the same place where is that boson. Так. And yeah, here are more. And now we came to the astrophysical constraints, which come from astrophysics. So supernovae, blazars, active galactic nuclei, and other known astrophysical sources of neutrinos can test characteristic self-interaction scales up to orders of GeV, and they are the point sources of high energy and ultra high energy neutrinos, which can test neutrino self-interactions in different ways. The presence of neutrino self-interactions can modify the observed spectrum of high energy neutrinos at IceCube, at KM3net, at Baikal experiments. And this can happen due to the process which occur inside the source or while traveling to Earth. So on this picture, you can see some constraints from supernova, from blazar TXS, yeah, some cosmological constraints. Yeah, I think that yeah, I think that's it. So and so from this moment, I will start to dive into the work I've recently completed. One way to obtain constraints from astrophysical neutrino sources is to consider high energy and ultra high energy neutrinos scattering on cosmic neutrino background. So high energy neutrinos must travel tremendous distances from the source to the detector on Earth. And if we assume existence of neutrino self-interactions instead of free streaming, these high energy neutrinos may scatter on the cosmic neutrino background. which is pretty abundant. Its density is 112 particles per cubic centimeter per flavor. And it consists from relic neutrinos with the with very low temperature, about 10 to the minus 4 electron volt. So if something very high energetic will scatter on something that low energetic, like it will give a very distinct feature in the final spectrum. Or such a scattering will remove such a high energy neutrinos from the initial spectrum at all. And this is the way how the observation of astrophysical neutrinos can be used to constrain neutrino self-interactions. In this work, we will use 4 very known sources of high energy and ultra high energy astrophysical neutrinos, and also recent ultra high energy neutrino event from KM3net. I'm pretty sure that you heard about it. It's 220 PV. So I will tell you a bit about each of the source. So supernova 87 is also a very famous source of high energy neutrinos. It was detected by many experiments, and in this research I mainly used this source to compare my result with the previous literature to make a double check. Another 3 sources are active galactic nuclei and blazars, which were detected by IceCube. Neutrinos from the sources were detected by IceCube, by CalGVD, and KM3net. You can see on the slide the energies and distances. Blazars, they produce neutrinos in hundreds of TeV range, and they are around gigaparsec away from us. AGN has smaller energy and closer to us. And you will see how it affects the constraints a bit later. So this would be a bit technical. This is about how we calculate means, how we calculate constraints on neutrino self-interactions. In order to establish limits on neutrino self-interaction coupling constant, it's enough to observe a single neutrino from the flux. Our next step is to calculate the mean free path, which is the inverse of the interaction rate. And the detection of neutrinos from high energy neutrino source requires that the mean free path of neutrinos through the Cosmic Neutrino Background is compatible or greater than the distance to source. I want you to sit a bit with this thought because it's very important. So we set this condition to the mean free path to experience at least one interaction. Okay. Do you have any questions up to this moment, maybe about mean free path or something? Okay, then I will continue. So we considered sources of neutrino, high energy neutrinos, and now we will talk a bit about background. So we have 2 background regimes. Because we don't know the exact masses of neutrinos, we have to consider 2 background regimes, where neutrinos are non-relativistic and when neutrinos are ultra-relativistic. In the previous literature, because it is a quite simple and straightforward approach, non-relativistic regime was very well described. And in this work, we decided to consider ultra-relativistic regime, with which is like a task with a star, because it includes many complicated calculations. Yeah, so we have two background regime, and also in previous literature, people considered separately massless mediator limit and heavy massive mediator limit, where they neglected full mass dependency. And in this work, we want to consider full mass dependence to provide you with the knowledge about what happens in the intermediate mass region, where the resonance is usually happening. I will discuss the results we obtained from this approach for flavor universal coupling constant. We obtained exclusion plots for the coupling constant from the mediator mass for non-relativistic regimes and ultra-relativistic regimes. So on this slide, you can see what we got for non-relativistic regime. In non-relativistic regime, you have very distinct like dips or spikes due to S resonance. What is important is that as a toy as a toy neutrino mass, we took 10 to the minus 3 eV. And for non-relativistic regime, we covered a new mediator mass region, taking this recent very energetic KM3net event. And also we proved previous constraints on neutrino self-interactions. And I want to note that this vertical thick dashed line is Z boson mass. So we are interested in the region which lays below Z boson mass. Here you can see the same, but for ultra-relativistic regime, you still have dips due to S resonance, but it is not so much pronounced as in non-relativistic regime. Here we did several assumptions to ease our calculations. So we put the neutrino mass to 0. We averaged angles between incident and background neutrinos. This is very physical assumption. And we reduced Cosmic Neutrino Background distribution to Maxwell-Boltzmann. And I also forgot to mention that the regions above the curve are the regions of exclusion. On this slide, you see the comparison between ultra-relativistic regime and non-relativistic Cosmic Neutrino Background regime. So they can coincide with the proper choice of parameters, but in general, they differ from each other, especially in the region where the resonances happen. Yeah, okay. Do you have any questions up to this moment? No? Okay.
Yes, Maria. Do you assume some specific representation to the scalar or just a scalar singlet, or there is any assumption regarding the scalar that you use in the S channel?
I use vector boson as a mediator, but I think that it differs from scalar boson up to some constant when you calculate constraints.
And for vector, you only consider S channel. Do you consider extra particle, for example, maybe if you had sterile neutrinos, the effect of sterile neutrinos? Because you may have interaction of active neutrino, sterile neutrino, and maybe a heavy vector. And then you could have maybe also the channel, maybe the channel exchange, or you are considering without the inclusion of stellar neutrinos?
I consider coupling between active and active neutrinos, and I consider S channel and T channel and also U channel. So this is basically I consider electron antineutrinos coming from the high energy neutrino source, and they scatter on cosmic neutrino background, which consists of neutrinos of all flavors. And you have all the possible channels you can get from there.
Thank you. Daniel, do you have a question? You wanted to say something or not?
No question.
Please continue, Maria.
Okay. Another very important finding I made is that it is usually discussion about cutoff parameter is often neglected in the literature, and this cutoff parameter comes from when you integrate total cross-section. When you integrate differential cross-section over the range from -s to 0, there appears algorithmic divergences at -s and 0, which correspond to the situation when the particle carries away all the energy or retains all the energy. So such a neutrinos, they should be removed from the detectable flux. So to isolate this fraction of cross-section, it is we take a cut-off parameter. We call it here epsilon. And in this moment, I followed footsteps of Kolb and Turner with the pioneering work, and I say that this is physical cutoff, and its value should be defined by an experiment geometry. Yeah, and on the slide you can see so how much it varies in the small mediator mass region. So if you consider not proper cut, you can you can put either too aggressive constraints or too light constraints on your neutrino self interactions. Так. Here I show another important and I think is useful result for non-relativistic constraints on coupling constant. And this illustrates that non-relativistic regime is sensitive to the neutrino mass variation. And this plot demonstrates how the position of S resonance shifts with the change of neutrino mass. So in this scenario, we took the neutrino mass common universal for all flavors. And the natural logical step of this research would be to consider which features we get if we consider normal hierarchy or inverted hierarchy, how would this feature would look like, and etc. So that's it on flavor universal coupling constant, and now I have some result on flavor non-universal coupling constant. Flavor non-universal coupling constant, especially for tau neutrinos, is very well motivated by cosmological tensions, and on this slide you can see a comparison of non-universal coupling constant to flavor universal coupling constant, and they obviously differ, but not that much. I would even say not in a very undetectable way, but still. And in ultra-relativistic regime, we can see that the resonance feature are enhanced for flavor universal regime more than for non-flavor universal. And so I will finalize with the recent detection of KM3net event and how it affected neutrino self-interactions constraints. This is, I haven't published this result anywhere yet, so you are the first to hear it. As I mentioned before, because KM3net event is like the most energetic neutrino which has ever been detected, it gives the higher constraints on the neutrino self-interactions. The only problem with it is that we don't know what is the source of this event. But there are some regions and where we can assume where this neutrino came from. So I took various distances for galactic origin, for extragalactic origin, for some transient source origin, and you can see the variation of the constraints based on the distance, and the further the source, the more tighter constraints we have. Yeah, but this dynamic is very important, and in after the S resonance, you see these dashed lines. These are the lines where we say that our cutoff is almost zero. So they give you their even bigger constraints in a small mediator mass region. Yeah, this is the comparison with previous works. So on the left panel, I compared supernova signal with the Kolb and Turner pioneering work. I applied their methodology, and this perfectly coincides. And I also compared my work with the most recent work I found from, it's very good work from Christian Doring and Stefan Vogel. And we coincide with the, for heavy mediator mass region, but they applied a bit different methodology. Therefore, results differ in a smaller mediator mass region. So in short, in this work, we investigated a particular model of neutrino self-interactions with Dirac neutrinos and massive vector boson as neutrino self-interaction mediator. We obtained analytical formula for ultra-relativistic and non-relativistic cosmic neutrino background with the full mass dependence. We constrained neutrino self-interactions by high energy neutrinos propagating through cosmic neutrino background from supernova, blazar, and AGN neutrinos scattering on both non-relativistic and ultra-relativistic cosmic neutrino background. We constrained flavor non-universal neutrino self-interactions. We applied recent high energetic, ultra high energetic event to constrain neutrino self-interactions, and we obtained more precise analysis on the angle cutoff parameter for a given model. and we included intermediate mass region for neutrino self-interaction mediator, and we extended constraints up to the mediator mass of GeV scale. So this is literature, and yeah, thank you for your attention. Please ask questions if you have some.
Thank you very much, Maria, for the very nice talk. Question from the audience?
Hi, thank you for the nice talk. So I was just wondering, like, I missed some initial part of your talk, so I don't know if you had already discussed. But then, can these non-standard interactions of neutrinos can they also have some implications for these long baseline experiments, like for instance the like the matter effect, or those kind of.
That would be actually very nice to consider neutrino self-interactions in dense media. It can potentially give you some very interesting resonances. And like my idea was to make it in some astrophysical environments, like inside of the blazar jet, something like that.
Okay.
Because, yeah. But I think
so some dense medium, like you mean, like in this very hot dense objects.
Yes, because they also have pretty big neutrino density, which is would be very useful for this task. This is a very good question about long baseline neutrino experiments. I think I will dig into this.
Okay.
Any more questions? If there are no more questions, we thank Maria for the very nice talk. Thank you so much, Maria, for the very nice seminar.
Thank you for having me. So have a nice day. I'm gonna have a nice evening.
Thank you. Bye-bye. Yeah.
Bye-bye.
Bye. Bye.
Bye. Thank you very much.
Thank you.
Thank you. Bye. Please send greetings to Adam. How is Adam?
He's good. He knows I was giving seminar.
Please convey my regards to Adam Metana.
Yeah, thank you actually for inviting me. It was my first invited talk. Yeah. Okay. Have a good one. Bye-bye.
Bye. Bye, Maria.